Hello, this is Professor Esther Pearson, and welcome to Module 4, Chapter 6, Normal Probability Distributions. If you're reading the first addition to our textbook, the Chapter 6 is titled Continuous Random Variables, but it is the same material being covered. You'll be introduced to the normal distribution, find area under a normal distribution, find probability using a normal distribution, find values of a normally distributed random variable, and approximate a binomial distribution using a normal distribution. So let's get started. In Chapter 6, we're taking a look at normal distribution. A normal distribution is a continuous probability distribution for a given random variable, known as x, that is completely defined by its mean and standard deviation. The properties of a normal distribution are as follows. A normal curve is symmetric and bell-shaped. A normal curve is completely defined by its mean and standard deviation. The total area under a normal curve equals 1. The x-axis is a horizontal asymptote for a normal curve. Here we have a visual display of symmetric and bell-shaped curves. On our left, as you face the screen, you see a symmetric and bell-shaped normal curve. On the right, as you face the screen, you see a symmetric but not bell-shaped, so it's not a normal curve. Now we look at how a normal curve is completely defined by its mean and standard deviation. We can see from the pictorial an inflection point, and the inflection point on both sides of the mean is a point on the curve where the curvature of the line changes. The inflection points are located at a mean minus 1 standard deviation and mean plus 1 standard deviation. Here in this pictorial, we see that we will be looking at the total area under the curve, and that's equal to 1. As you look at the normal or bell-shaped curve on your right, you can see that the total area under the curve equals 1. The normal curve on the left, you can see that it is possible to make a measurement that doesn't include the total area under the curve. So let's see how we do that. Now for some preliminaries, we see that our bell-shaped curve on the left as we face the screen is correct. The axis, that is the x-axis, is a horizontal asymptote, meaning that the tails of the curve come near but don't touch our baseline. The visual display on the right as you face the screen indicates that it is incorrect. We don't have an asymptote, a horizontal asymptote, as you see that the tails of the curve cross the baseline, indicating this is not a representation of a horizontal asymptote of the x-axis. So let's determine if the following is a normal distribution. We'll take a look at birth weights of 75 babies. Yes, that would be a normal distribution. Next, we'll take a look at ages of 250 students in the 10th grade. No, this would be uniform, not the bell-shaped curve. Next, let's take a look at heights of 100 adult males. It would be a normal distribution. And then the frequency of outcomes from rolling a die. No, because the data is discrete. What about the weights of 50 fully grown tigers? That would be a normal distribution. Looking at those examples, what do you notice in terms of which distributions were normal and which ones weren't? Note the characteristics that will be helpful for you going forward. Looking at the pictorial, the question arises, how many normal curves are there? Because there are an infinite number of possibilities for mean and standard deviation, there are an infinite number of normal curves. We can see at the pictorial that the characteristics of a normal curve or a bell-shaped curve are in all of those pictorial curves. Some are just more closely gathered around the mean than others. Now, having looked at a normal distribution, let's take a look at a standard normal distribution. A standard normal distribution has the same properties as the normal distribution. In addition, it has a mean of 0 and a standard deviation of 1. So for properties of a standard normal distribution, the standard normal curve is symmetric and bell-shaped. It is completely defined by its mean and a standard deviation. The mean equals 0 and the standard deviation equals 1. The total area under a standard normal curve equals 1. And lastly, the x-axis is a horizontal asymptote for a standard normal curve. So how do we convert to the standard normal curve from a normal curve? The standard score formula is known as the z-score. The z-score equals a data value minus the population mean divided by the standard deviation. When calculating the z-score, be sure to round your answers to 2 decimal places. Now let's draw a normal curve given the mean equals 40 and the standard deviation equals 5. Indicate the mean, each of the inflection points, and where each given value of x will appear on the curve. X sub 1 equals 33 and x sub 2 equals 51. So for our solution, we see our curve, and we've got our mean of 40 and our standard deviations of 5. So we can draw our data point of x sub 1 at 33 and our data point of x sub 2 at 51. Now let's convert to the standard normal curve. Given a mean of 40 and a standard deviation of 5, calculate the standard score for each x value or data value and indicate where each would appear on the standard normal curve. X sub 1 equals 33 and x sub 2 equals 51. So for our z-score sub 1, we have 33 minus 40 divided by 5. So that would be our data value x sub 1 is 33 minus our mean of 40 divided by our standard deviation of 5. And that would give us a z-score, z sub 1, of a negative 1.4. Next, let's take a look at our z sub 2 or z-score for our data value 2. And that would equal 51 minus 40 divided by 5. 51 is our data value x sub 2. minus 40, which is our mean, divided by 5, which is our standard deviation. So our z-score sub 2 equals 2.2. Now let's draw the values. For our standard normal curve, we know that our mean equals 0 and our standard deviation equals 1. So 0 plus 1 standard deviation and 0 minus 1 standard deviation. Now we can plot our z-scores. Z sub 1 is plotted at a negative 1.4 and z sub 2 is plotted at 2.2. Now let's take a look at another example where we convert to the standard normal curve. Given our mean equals 48 and our standard deviation equals 5, convert to a normal curve and indicate where a score of x equals 45 would appear on each standard normal curve. So for our solution, we draw our curve and we put in our mean at 48 and our standard deviation is 5, so 48 plus 5 would give us 53, 1 standard deviation above the mean, and our standard deviation below the mean would give us 48 minus 5, or 1 standard deviation below the mean would be 43. And now we can plot our data value of 45. Let's continue on. We determine our z-score by taking our data value of 45, subtracting it from the mean of 48, and dividing it by our standard deviation of 5. That gives us a value of a negative 0.6. Now we can plot that value for our standard normal curve, where our mean would equal 0 and our standard deviation would equal 1. 1 standard deviation above the mean and 1 standard deviation below the mean, and we plot our z-score at a negative 0.6. Now let's take a look at a probability of a normal curve. The probability of a random variable having a value in a given range is equal to the area under the curve in that region. I'll read that one more time. The probability of a random variable having a value in a given range is equal to the area under the curve in that region. And here we have a pictorial where we've got a mean of 75 and a standard deviation of 5. So 1 standard deviation above the mean would give us a value of 80. And so now we can plot the area under the curve and plot our random variable. And here we have it at 0.1587. Now let's take a look at how we find values using a standard normal distribution table. And we see the table there in the center of our PowerPoint slide. It's entitled Standard Normal Distribution Table from a negative infinity to a positive z. Across the top of the table on our horizontal row, we see a z-scores 0.00, 0.01, 0.02, and 0.03, and 0.04. On our vertical column, for our z, we see 0.0, 0.1, 0.2, down to 0.8. And as our vertical and our horizontal rows and columns intersect, we have values. For example, on our z column at 0.0, 0.0 and across horizontally at 0.00, we see the value of 0.5000. Let's continue on taking a look at the standard normal distribution table. Now, the standard normal tables reflect a z-value that is rounded to 2 decimal places. The first decimal place of the z-value is listed down the left-hand column. So that would be our vertical column on our left-hand side. The second decimal place is listed across the top row. Where the appropriate row and column intersect, we find the amount of area under the standard normal curve to the left of that particular z-value. So when calculating the area under the curve, be sure to round your answers to 4 decimal places. Now let's take a look at the area to the left of our z-value. Finding the area to the left of the z-value, let's take an example of z equals 1.69. And on our table, that would give us a value of 0.9545. Taking a z-value of a negative 2.03 on our table, that would give us a value of 0.0212. On our table, a z-value of 0 would give us 0.5000. A z-value of 4.2 on our table would give us approximately 1, the entire area. A z-value of a negative 4.2 would give us approximately 0. Take a look at the chart in your table and these z-values and see if you can find the area to the left of z. Now let's take a look at the use of technology. We're using an example of a Ti84 Plus and the instructions. First, you would press the second key, then the vars. Choose 2, and that would be the normal CDF. The format for entering the statistics is normal CDF minus, parenthetically, minus 1E99, comma Z, close paren. In the previous example, part A, we could have entered the normal CDF, open paren, minus 1E99, comma 1.6.9, close paren, and that would have indicated our value. Now let's take a look at the area to the right of Z. Now let's take a look at finding the area to the right of Z. For example, Z equals 3.02. The area to the right would be 0.0013. For a Z value of a negative 1.70, the area would be 0.9554. For a Z value of 0, the area would be 0.5000. For a Z value of 5.1, the area to the right would be approximately 0. And for a Z value of a negative 5.1, the area to the right would be approximately 1. Let's see if you can find those values using your table. Now let's see how we can find our values using our Ti84 Plus. First, you would press the second key, then vars. Next, you would choose 2. normal CDF open paren. The format for entering the statistics is normal CDF open paren Z, 1E99 close paren. In the previous example, part A, we could have entered normal CDF 3.02, 1E99 close paren, and that would have given us our answer. Next, let's take a look at the area between Z sub 1 and Z sub 2. Finding the area between Z sub 1 and Z sub 2. So if Z sub 1 equals 1.16 and Z sub 2 equals 2.31, we would find the area, and that would be 0.1126. For another example, with Z sub 1 equaling a negative 2.76 and Z sub 2 equaling 0.31, the area between Z sub 1 and Z sub 2 would be 0.6188. If we have a Z sub 1 of a negative 3.01 and a Z sub 2 equaling a negative 1.33, the area between Z sub 1 and Z sub 2 would be 0.0905. Next, let's take a look at how we can use our technology, our Ti84 Plus. First, we would press the second key, then vars. Choose 2, our normal CDF open paren. The format for entering the statistics is normal CDF open paren minus 1E99, comma, Z sub 2 close paren. Then we would select a dash there and then repeat steps 1 through 3. This time entering the statistics as normal CDF open paren minus 1E99, comma, Z sub 1 close paren. In the previous example, part A, we could have entered normal CDF open paren minus 1E99, comma, 2.31, which was our Z sub 2, minus a normal CDF open paren minus 1E99, comma, 1.16, which was our Z sub 2, and that would have given us our answer. Take advantage of the technology that's available to you. Now let's take a look at how we find the areas in the tails. We can see the shaded blue area for Z sub 1 in the tail and the shaded area of Z sub 2 in the tail. So let's see how we find the area in the tail with an example. If Z sub 1 equals 1.25 and Z sub 2 equals 2.31, that would give us a value of 0.9048. Note, we're using our technology. Another example, Z sub 1 equals a negative 1.45 and Z sub 2 equals a negative 2.40. The areas in our tails would be 0.6188. One more example, with Z sub 1 equaling a negative 1.05 and Z sub 2 equaling 1.05, using our technology, the area in the tails would be 0.0905. Let's take a look at our technology, our Ti84 Plus instructions. Press the second key, then vars. Choose 2, our normal CDF open paren. The format for entering the statistics is normal CDF open paren minus 1E99, comma, Z sub 1 close paren. Select plus. Repeat steps 1 through 3, this time entering the statistics as normal CDF, Z sub 2, comma, 1E99 close paren. Now in the previous example, part A, we could have entered normal CDF minus 1E99, comma, 1.25, close paren, plus normal CDF, open paren 2.31, comma 1E 99, close paren, to find our answers. Here in our last slide we have some pictorials of finding area. And we can look up Z, look up negative Z in our top two pictorials. And in our bottom two pictorials, we can look up Z sub 1 and negative Z sub 2 and add. And then we can look up Z and subtract Z sub 1 from Z sub 2. So in our top two pictorials, we can see we're finding the area to the left. Next, we're finding the area to the right. And then on our bottom two pictorials, moving left to right, we can see that we're finding the areas in the tails. And in our last pictorial, we can see we're finding the area between Z sub 1 and Z sub 2. This is a helpful group of pictorials in terms of thinking about the concept of finding the area under the curve.